The presentation is titled, Balun Design. This work explores the design and functionality of a balun, focusing on exploring different types of baluns and their implementations inside Keysight Genesys. This presentation will cover the following topics: an introduction to baluns, the Lange coupler-based balun design, simulation and practical implementation using Keysight Genesys, transformer-based balun explanation and simulation, lumped elements-based balun explanation and simulation, quarter-wave coaxial-based balun explanation and simulation, half-wave lines-based balun explanation and simulation. Let's dive in. A balun, or balanced-to-unbalanced transformer, is used to convert signals between balanced and unbalanced transmission lines. A balanced line has two conductors with equal potential but opposite phases. An unbalanced line has a single conductor with a ground reference. Baluns are commonly used in RF and microwave systems for impedance matching and maintaining signal integrity. A Lange coupler-based balun uses two Lange couplers arranged back-to-back. The input at port 1 receives an unbalanced signal. Outputs at ports 2 and 3 provide balanced signals, with a phase difference of 180 degrees. This configuration achieves an equal power split while maintaining isolation between the outputs. The schematic demonstrates the design of the balun using two Lange couplers. It highlights ports for input and output signals, transmission lines for signal paths, coupling regions where power is distributed. This layout is key to understanding the balun's operation. The Lange coupler uses tightly spaced interdigitate microstrip fingers for power coupling. Key design parameters include: the width, represented by the symbol W, defines the microstrip line's thickness. The spacing, denoted as S, specifies the gap between the fingers. The length, represented by L, determines the total coupler size. Performance metrics for scattering parameters include: forward transmission, or S21, ideally at -3 decibels. Isolation, denoted as S31, typically targeted at -8 decibels to minimize interference. The layout showcases the balun's physical implementation, including metal layers for signal pathways, bridge connections that ensure signal continuity, coupled line sections for effective power splitting. The first Lange coupler splits the unbalanced input signal into two components. The second Lange coupler finalizes the power division and introduces a 180-degree phase difference. The scattering parameter S21 describes the signal path from input to the primary output, while S31 quantifies the isolation between outputs. The result is balanced outputs at ports 2 and 3 with equal amplitudes but opposite phases, ensuring precise power division. Implementation in Keysight Genesys requires two substrate layers and two metal layers. Dimensions such as width W of 726 nanometers and length L of 4.089 millimeters. A metal bridge positioned on the topmost layer. Configuration supporting 4, 6, or 8 microstrip fingers for flexible coupling designs. The balun is designed to meet the following performance goals: forward transmission, S21, at -3 decibels. Isolation, targeted at -8 decibels to minimize interference. Impedance matching at 50 ohms for the input, with 25 ohms at each output port. These parameters ensure optimal signal distribution and minimal losses. In conclusion, the Lange coupler-based balun successfully achieves its theoretical objectives of balanced output, phase splitting, and power division. The scattering parameters S21 and S31 validate its performance. Tools like Keysight Genesys facilitate accurate implementation, making this balun design invaluable in RF and microwave systems. Now this is the part on designing a balun using a Lange coupler in Keysight Genesys software. Let's dive into the steps. Let's begin with the first step. Select the Start page from the menu and then choose Signal Control. Next, open the Signal Control Properties window and select Balun. Moving on, set the substrate for the balun. Choose Rogers RO3003 as the substrate. Now, go to the Settings section. Set the frequency band to range from 7 to 8 GHz. After that, navigate to the Options section. Check the box for Create Layout. Then, select Manufacturing Process, and choose Microstrip Standard. Once that's done, head over to the optimizer. Check the desired values for your goals, then click Calculate Now, and wait for the structure to be optimized. The next step is to implement the structure on a PCB with 2 substrate layers. Right-click on the Layout window and select Layout Properties. In the Layout Properties window, go to the Layers tab, click Load from Layer File, and open the file named lang.lyr. Here's what you do next. Click on Show All. In the Use column, check Top Metal and the substrate beneath it. Then, click OK. Now, let's change the layer of the Lange coupler. Modify the layer for the coupler and the ports from Bridge Metal to Top Metal. Once all parts are ready, select the entire layout. From the Layout menu, choose Connect Selected Parts. Then, click Center Selected on Page. Don't forget to save your design. Finally, to view the 3D geometry, right-click on the Layout window and select View 3D Geometry. In conclusion, the Lange coupler-based Balun successfully achieves its theoretical objectives of balanced output, phase splitting, and power division. The scattering parameters S21 and S31 validate its performance. Tools like Keysight Genesys facilitate accurate implementation, making this Balun design invaluable in RF and microwave systems. This slide introduces the transformer Balun, a simple and effective device for converting signals between balanced and unbalanced lines. It uses a transformer with a single input winding to handle the unbalanced input. The balanced output is provided through a center-tapped secondary winding. Transformer Baluns are typically used in low-frequency applications, operating at frequencies up to 1 GHz. The schematic demonstrates the operation of a transformer Balun. The unbalanced input is connected to the primary winding. The balanced output is taken from the center-tapped secondary winding. Key parameters such as inductance and the coupling coefficient play a critical role in the balun's performance. The transformer balun exhibits the following key features: unbalanced input, the primary winding connects to the single-ended input. Balanced output, the secondary winding provides two signals with equal amplitude but opposite phases, via its center tap. Impedance matching, the input is designed for a characteristic impedance of 50 ohms. The balanced outputs typically have an impedance of 25 ohms each. It is best suited for applications operating below 1 GHz. The performance and applications of transformer baluns include performance metrics, low signal loss and high isolation between output ports. Precise phase and amplitude balance between the balanced outputs. Applications, widely used in radio frequency front ends for impedance matching and signal conversion. Commonly applied in systems operating at frequencies up to 1 GHz. Practical design considerations for transformer baluns include transformer design. The inductance of the windings is crucial. For example, the primary inductance may be 957.7 nanohenries. A coupling coefficient close to 0.99 ensures efficient power transfer. Frequency response, optimized for low-frequency applications. Performance deteriorates at higher frequencies due to core losses and parasitic effects. Select the class of the balun. Choose transformer. Now, make sure to check this. Ensure the self and mutual inductance of the transformer elements are tunable. Let's move to the Settings section. Here, set the frequency band to range from 100 to 200 MHz. The next step is to optimize the circuit. Go to the optimizer and adjust the goals. Change the return loss target from 20 dB to 10 dB. Here's what you do next. Navigate to the Variables tab and click on Get Tuned Variables. Finally, click Calculate Now to optimize the circuit. Once the optimization process is complete, your balun design using a transformer is ready. The transformer balun offers several advantages: a simple and robust design, high efficiency, especially for low-frequency operations, excellent impedance matching between input and output, Minimal signal distortion due to low parasitic effects at lower frequencies. In conclusion, transformer baluns are highly suitable for applications that require balanced outputs at lower frequencies, up to 1 GHz. Their simplicity, efficiency, and ability to achieve precise impedance matching make them indispensable in many radio frequency systems. Proper design ensures accurate phase and amplitude balance for optimal performance. This slide introduces the lumped-element balun, which uses discrete components like capacitors and inductors to perform the functions of a balun. It is often implemented as a lumped version of a rat race coupler. The design achieves a positive 90-degree phase shift at output port number 2, a negative 90-degree phase shift at output port number 3. The resulting phase difference between the two output ports is 180 degrees. The schematic illustrates how the lumped-element balun implements the functionality of a rat race coupler. Inductors, represented by LL, and capacitors, represented by CC, are used for impedance matching and phase shifting. The input signal is split into two balanced outputs, with a phase difference of 180 degrees. This schematic highlights the simplicity and efficiency of using lumped components for this purpose. The lumped-element balun offers several key features. Phase relationship: port number 2 has a phase shift of positive 90 degrees relative to the input. Port number 3 has a phase shift of negative 90 degrees relative to the input. Output balance: the phase difference between the outputs at ports 2 and 3 is 180 degrees. This ensures a proper balanced output. Isolation: at the isolated port, signals from different paths cancel each other, minimizing signal leakage. The performance and applications of the lumped-element balun include: performance: it provides accurate phase shifts and ensures signal balance. Effective isolation is achieved at the unused port, minimizing interference. Applications: suitable for compact radio frequency designs where lumped components are preferred over distributed elements. Commonly used in low-frequency applications where size and cost are critical considerations. Practical design considerations for the lumped-element balun include: component selection: inductor and capacitor values must be carefully calculated based on the operating frequency. High-quality components help minimize losses and reduce phase errors. Frequency limitations: the balun is suitable for low to mid-frequency applications. At higher frequencies, parasitic effects can degrade performance. Layout design: a compact layout reduces unwanted coupling and enhances performance. The lumped-element balun provides several advantages. Its compact design makes it ideal for integration into small systems. It is a cost-effective solution for low-frequency radio frequency systems. It delivers accurate phase balance and impedance matching, ensuring reliable performance. Now to the third part of this tutorial, designing a balun using lumped elements in Keysight Genesys software. Let's jump in. Let's start with the first step. Go to the Topology section and select the class as Lumped. Next, set all the components in the design as tunable to allow for optimization. Now, head to the optimizer. In the Variables tab, click on Get Tuned Variables. Here's what comes next. Click on Calculate Now to begin the optimization process. That's it. With these steps, you've successfully designed a balun using lumped elements. In conclusion, lumped element baluns offer a compact and simple solution for converting signals between balanced and unbalanced formats. They achieve the desired 180-degree phase difference between outputs with minimal signal loss. These baluns are best suited for low-frequency applications where size and simplicity are critical design priorities. Now to the fourth part of this tutorial, designing a balun using quarter-wave coax in Keysight Genesys software. Let's get started. To begin, navigate to the Topology section and select the class as Quarter-Wave Coax. Next, head over to the Optimizer. In the Variables tab, click on Get Tuned Variables. After that, click Calculate Now to optimize the circuit. Now, let's set the frequency. Go to the Settings section and specify the frequency band. Set it to range from 1000 to 2000 MHz. Moving on, check your optimization goals and variables. Once confirmed, click Calculate Now again to finalize the design. That's all for this section. You've now designed a balun using quarter-wave coax. This schematic demonstrates the half-wave balun design. It consists of transmission lines with a characteristic impedance of 50 ohms. A key component is the 180-degree delay line, labeled as TL3, with a characteristic impedance of 100 ohms. At the output ports, the signals have a 180-degree phase difference, ensuring balanced output. The half-wave balun has the following key features: phase difference, one output signal is delayed by 180 degrees relative to the other. Transmission line design, transmission lines TL1, TL2, and TL4 have a characteristic impedance of 50 ohms. The delay line, TL3, has a characteristic impedance of 100 ohms and an electrical length of 180 degrees. Output balance, the balanced output signals have equal amplitude but opposite phase, ensuring proper signal integrity. The performance and applications of the half-wave balun include: performance, provides an accurate 180-degree phase shift between outputs. Exhibits low loss in the transmission lines, ensuring efficient signal transfer. Applications, used in radio frequency systems requiring precise phase-balanced outputs. Ideal for high-frequency applications where distributed transmission lines are preferred over lumped components. Practical considerations for designing a half-wave balun include: transmission line parameters, ensure the transmission lines have the correct characteristic impedance and electrical length for the target frequency. The 180-degree delay line should use a 100 ohm impedance line. Frequency dependence, performance is dependent on the operating frequency due to the phase delay mechanism. Material considerations, use low-loss materials to minimize signal attenuation at high frequencies, maintaining efficiency and accuracy. The half-wave balun offers several advantages. Its simple design is based on distributed transmission lines. It is highly effective for high-frequency applications, where distributed components excel. It ensures accurate phase balance between the output signals, providing reliable performance in critical RF systems. Now to the fifth part of this tutorial, designing a balun with half-wave lines in Keysight Genesys software. Let's get started. First, go to the Topology section and select the class as half-wave lines. Next, move to the Settings section. Set the frequency band to range from 1000 to 2000 MHz. Now, let's prepare for optimization. Set all variables as tunable. Then, in the optimizer, add these tunable variables and click Calculate Now. After that, go to the Options section. Check the box for Create a Layout and select Microstrip Line Standard. Finally, head over to the Layout tab. Select all parts of the layout and choose Connect Selected Parts. Then, click Center Selected on Page. And there you have it. You've successfully designed a balun with half-wave lines. In conclusion, the half-wave balun achieves balanced outputs with opposite phase using a 180-degree delay line. It is ideal for high-frequency radio frequency applications requiring precise phase relationships. Proper design and careful implementation of the transmission lines ensure minimal loss and high performance. Thank you for watching this tutorial on designing baluns in Keysight Genesys software. We hope you found this content helpful and engaging. If you enjoyed this video and want to learn more about RF design, microwave engineering, and simulation techniques, make sure to hit the like button and subscribe to our channel. Don't forget to turn on the notification bell so you never miss an update. Your support helps us create more high-quality tutorials just for you. Thank you again, and we'll see you in the next video.